Yeah, so let us get started. So we are discussing on this topic, and I'll straight away go to the topic where we started yesterday and briefly recapitulate from that point. So you understood that for continuous torque production we need two magnetic fields, and the two magnetic fields have to be uh, stationary with respect to each other with some angular shift. So we saw the possibilities. So we understood that um, we can either we have two ways of realizing the stator magnetic field. One is stationary, another is rotating. So yesterday we saw that if we have this type of a structure, and if we excite with DC current, then in space, in the air gap, we will have some magnetic field. Because the current is constant, the magnetic field will also not change with time. Then we looked at that if we vary the current, then the magnetic field will change. Like this, it will modulate its amplitude, and it will flip also. Then we realized that uh, using three phase, it is possible for us to produce a rotating magnetic field. All these are using concentrated winding. um, Now this same thing can be done with distributed winding also, like as shown in the right hand side picture. So we also visualized what we mean by concentrated coil and what do we mean by distributed winding. So distributed winding, if we excite by three phase current, then we understood that it will produce a rotating magnetic field in the same way. So we understood that we understood how it produces rotating magnetic field. Now we looked at different instances, and after that we looked at how the field traverses as we move ahead in time. We saw that with higher number of slots, it is possible to uh, reduce the harmonics in B distribution. That is what are called as space harmonics. It is possible to reduce them. And we looked at how to make winding for that. Say a 24 slot two pole machine, we saw how it rotates. And then the same thing, if we have to do for a four pole machine, we understood how to make winding to just get four poles out of the same stator structure. We understood that we are able to create four poles in in the same structure by just changing the way we wind the coils. And uh, we visualized the four poles, four pole rotating magnetic field, where you have four axes, which are four poles which are rotating continuously with time. Then we also understood the difference between electrical and mechanical angles. So because in the two pole machine, with the completion of one electrical cycle, the magnetic field distribution in the air gap, that also completes one complete rotation. So electrical cycle is same as mechanical cycle. So electrical angle is also same as the mechanical angle in two pole machine. But as we go for a four pole machine, then we saw that with completion of one electrical cycle, the in space, in the air gap, the B distribution only rotates by 180 degree. That is, it rotates by, it completes half a rotation. So we understood that electrical angle in this case has to be twice compared to the mechanical angle. So from there we also understood the relationship between electrical angle and mechanical angle, that has to be multiplied by the pole pairs, number of pole pairs. So we saw all these things till the last day's class. So today uh, we'll to create the second magnetic field. So as discussed already, there has to be two magnetic fields, say F stator and F rotor. So these two have to be relative with relative speed 0 with respect to each other. So if we understood that there are two ways. One is if both are stationary, that is if omega this um, omega r can be confused with the actual mechanical speed. So omega, I'll say fr, and this is omega fs, that is the speed of the magnetic fields. So one possibility is if both are stationary. So we understood if omega fr is equal to omega fs equal to 0. So for this case we understood how to get a stationary stator magnetic field. Now a corresponding thing can be how to produce a stationary rotor magnetic field. What is the challenge here? Challenge is the rotor itself is moving. So that means the conductors on the rotor, they are also moving. So the conductors on the rotor has to move, but in space the magnetic field produced by the rotor should remain stationary. That is the challenge here. So we'll see that. Next, there is another possibility of if omega fr equal to omega fs. Both are equal, they have to be equal, and they are equal at some speed called as omega s. Let us say that is the synchronous speed, or the speed corresponding to the electrical frequency in the stator. So you also understood that frequency, if frequency equal to 50 hertz, 50 hertz means 50 cycles per second. So if we have to convert it with to rpm or rotations or cycles per minute, then we have to multiply it by 60. So it will become 3000 rotations per minute or cycles per minute, whatever. So this is equal, this is corresponding to the synchronous speed omega s. So omega, generally in general notations it is always in radian per second, but yeah, bear with me for these things. So this thing has to be just multiplied by that number 2 pi by 60 in order to get the omega, that is the angular speed in radian per second. So the second way of getting or having continuous torque is both magnetic fields are rotating and they are at the same speed. So let us see how to produce that. So this is the first one, DC current in this is the first way of realizing it. So we can put DC current into the rotor, and the rotor can rotate at the speed of the stator magnetic field. We'll visualize it what happens. Then the next possibility can be we will inject so both will rotate. So rotor will also rotate and magnetic field will also rotate with respect to rotor, and the addition, the excitation frequencies and the speeds will be in such a way that the relatively with respect to a stationary observer, that speed will become equal to the stator magnetic field speed. So that is the second way. And the third way is of course the case for the first case, that is Roman 1, what I have indicated. We can inject a DC current into the rotor rotates, but the rotor magnetic field remains stationary with respect to the stator. So that is the case for or let us leave that as of now, which one is which motor, that will realize as we go forward. So these are the three ways by which we can realize some rotor magnetic field. So let us go to the first case. So in this case the stator remains the same and I am not exciting it. So the stator, whatever is shown in gray color, and the windings whatever which are shown in gray color too, they are not excited at all. We have some pole, some rotor which is of this shape as I have indicated, and we have some conductors on the rotor. So we wind, so we have this structure, this is the pole structure, right? This is the pole structure what we have, and we also have some winding in this, we have some winding in this region. So in this region we have some winding, in this region we have some winding, similarly in this region we have some winding, in this region we have some winding, all the on the pole body. And how are we winding it? We are putting all dot conductors here and cross conductors here. So if say we have our winding like this, where current, some current is coming like this, then they will go like this and come out from this other side. So this will be the winding sense, right? I hope you get it. Then similarly for this case also, it has to again go in, because this is cross and this is dot, so it will come out from this side, and in this way the complete winding will be made and the current will come out of it. So this is how we make the rotor winding. So this is shown in this left hand side picture, and if we actually pass some current into it and try to look at how the field will look like, then you can see that this right hand side picture shows the field line distribution. So you can see that clearly there is some axis. So if this is dot and this is cross, so then obviously flux lines will come out from this. That means it will become a north pole for us, and flux lines will come into this, so it will become a south pole, the rotor surface, right? So this is how it will look like. So in all these cases, these flux lines are actually going out like this, and here these are coming in like this, and they are crossing the air gap, they are entering the stator through these different stator teeth, and they are flowing on the two sides through the yoke and completing their path like this. So these are this is about the flux line distribution. And um, if I try to make the axis of the magnetic field, I'll probably erase the lines which I have drawn to avoid any confusion. Then we remember our definition of magnetic field axis. Magnetic field axis is that line which is not crossed by any flux line. So we can see that here half the flux lines are going this side, left hand side, and half the flux lines are going in this side. So if we draw a line in between, so that is the axis, of the magnetic field, right? This is the axis. So even if it is intersecting some of these lines, that is because of the inaccuracies of my drawing. This line is not intersected by any of the flux lines. So this is the magnetic field axis. Now you can see the rotor is rotating, or rotor is stationary in this case, and we have a stationary magnetic field. Now what happens if we rotate the rotor? So the rotor rotates by how we don't know, but somehow the rotor rotates, or we make the rotor rotate by some prime mover, let us say. What happens? We are just trying to see what happens if the rotor rotates. So here is one animation that I will run. So you can see the rotor rotates, the currents into the winding of the rotor remains same. It is a DC current that is passed through that, and with the rotor the magnetic field also tends to rotate in space in the with the same speed. So because we are stationary, we are looking from a stationary reference frame, because we ourselves are stationary. So or how the stator looks at it. So probably I'll stop at multiple instance and help you see that. Yeah, so this is the initial instant. Now if I move ahead by some move ahead by some time, you can see that initially the axis was here. Now with rotation, the axis has actually shifted to this point. Now further, if I move, the axis has shifted here. If further I move, the axis has shifted here. Here again the axis has shifted here. So again here at this point, the axis has come back to its zero position. I'm not sure whether you are able to see this time also, which is quite small. So it started from 0 millisecond or 0 time, and it has completed one rotation. The magnetic field has completed one rotation in 20 millisecond, which is corresponding to 50 hertz. The time corresponds to 50 hertz. The period for a 50 hertz sinus periodic signal. And the rotor actually rotates. So what the rotational speed that I have given for the rotor, the mechanical speed, that is actually 3000 rpm. So you know that 3000 rpm in frequency, it corresponds to 3000 by 60, that is 50 hertz. So by injecting a DC current into the rotor and by rotating the rotor at some speed, we can have a rotating magnetic field generated by the rotor. Now this is how we can have now if you see, we already have a three phase distributed winding in the stator that produces a magnetic field, that produces a stator magnetic field that is always rotating at synchronous speed, that is the speed corresponding to the electrical frequency, that is 3000 rpm for 50 hertz current excitation. Now the rotor, if we inject some DC current into the rotor and rotate the rotor at 3000 rpm, then we create another magnetic field Fr that is not rotating because of alteration of current, but because that is rotating because the rotor itself is rotating and the coils are also rotating with it. That is why the second magnetic field, that is also rotating at the same speed as the rotor speed, omega r, that is the rotor speed, that is equal to the speed of the rotating magnetic field. So this is how we can create two magnetic fields which are stationary with respect to each other, and there is some angle in between. So this is, so you can see that this is the simplest of machines, or which is known as synchronous machine, simplest to realize. If we think in these terms, we can create a rotating magnetic field by we know how to produce a rotating magnetic field by distributing the winding and then injecting three phase current into that. That will produce a rotating magnetic field that we know. Now we can inject DC current into the rotor. We can make some winding in the on the rotor and we can inject DC current into it. That produces a stationary magnetic field in the rotor. Now if the rotor itself rotates at the synchronous speed, or the speed at which the magnetic field produced by the stator rotates, we can make the rotor magnetic field also rotate. And if we can ensure some phase angle between the two, which is also known as the torque angle, that is nothing but the angle between the two magnetic fields, then we can produce some non-zero torque, non-zero constant torque. Now what happens if the two magnetic fields are the angle between the two magnetic fields, say let me call it as delta. What if delta is equal to 0? Then there is no torque production, torque equal to 0. That means the motor is running but it is not delivering any torque, it is running under no load. And if delta actually increases to some positive value, then there will be a positive or negative torque based on which one leads and which one lags. Then we will have some motoring action or generating action. So the basic principle is if we have two magnetic fields, say Fs and Fr, and the rotor itself, rotor is something, so the rotor is rotating at anti-clockwise, then which one is leading? Fs is leading Fr. Then power transfer is happening from stator to rotor, that is it is motoring. So power transfer is happening from stator to rotor, that is power, electrical energy is getting injected from the stator, and it is getting converted into mechanical energy and making the rotor to rotate. But if we have two magnetic fields with the rotor still rotating at anti-clockwise direction, if we have the rotor magnetic field that leads the stator magnetic field, then actually power transfer is happening in the opposite direction. So basic idea is whichever magnetic field leads, power transfer happens from that to the lagging thing. If the stator magnetic field leads, that means power transfer is happening from stator to rotor, and if rotor magnetic field leads, then power transfer happens from rotor to stator, that is a generating action. That is, a prime mover is rotating the rotor, and that is converting the mechanical energy into electrical energy, and electrical energy is going out from the stator winding. So this is the first most simplest realization of an electrical machine that turns out to be synchronous machine, what we know as synchronous machine. Now you may ask that something is rotating, how can we inject current, how can we make electrical connection to it? So I'll just give a brief uh, demonstration of that by, of course, drawing some picture. Probably I'll erase this portion. Yeah. So say we have a shaft. We have some. This is a pole. This is a simplified case. This is the rotor, and somehow I have one terminal of the coil that is coming here, and another terminal, they say it is coming here. Now say we have some rings mounted on the rotor itself. So this is the first ring, and we can have a second ring also. So the rings are basically put on the shaft itself. That means the rings are also rotating. Now what we do, and the rings are conductive in nature. So what we can do is connect one terminal to one ring and another terminal to another ring. So the entire thing is rotating now. The rotor itself is rotating, the rings are also rotating, and with that the windings connected to the rings, they are also rotating. So there is no problem here. Now if we have some ring like this is the outer surface of the ring, we can always connect some mechanism, so something like this, which is always touching the ring. So although the ring is rotating like this, there is always some contact here, and this can be taken out. So this is for the ring 1, and similar thing can be there for ring 2 also. Some mechanism that is always touching the ring, and from there the two terminals can be taken out. So this is known as slip ring. So that is how we can make electrical connection into any rotating body. although the rotor is rotating and the windings are also rotating. So how do we make connection? We can use some mechanism like this. So this is about uh, realization of a rotating magnetic field from the rotor by injecting some DC current into the rotor winding. And we have seen that if the rotor itself rotates at the same speed of the compare as the same speed of the synchronous speed, then we can have two stationary magnetic field with respect to each other. So because stator magnetic field is also rotating at omega s, rotor magnetic field also rotating at omega s, so they are stationary with respect to each other. And we briefly understood the principle of uh, power transfer. So whichever magnetic field leads, power transfer happens from that to the lagging one. Now actually we can realize the rotor magnetic field in two ways. So in the earlier case, whatever we have seen is we have some poles, this structure is known as salient pole because there are some poles. So we have non-uniform air gap. We have very zero air gap, very small air gap in this region just under the pole. But in the uh, uh, in the non-polar region, whatever what is that called, in this zone, just uh, 90-degree away from the poles.
Interpolar region.
Interpolar region, correct. So interpolar region, there is a larger air gap, right? This is one realization. But we can also have a cylindrical structure. So we can this is a picture that I show here. So the same thing, you can see that we can have a north pole and the south pole by putting winding like this. So this side it is dot, it is cross here, so all dot and cross appear like this. So the effective magnetic field becomes like this. So this is how they complete their path. All these are closed lines, of course, right? So this is how the rotor magnetic field would look like. And if the rotor is made to rotate, then we would be able to produce a rotating magnetic field running at the rotating at the same speed as the stator magnetic field. And another next thing, what we have already seen, this is shown for a four pole case. So in this case we have four poles, one north pole here, one south pole here, again the north pole here and the south pole here. So this would be okay for a four pole. If we have a four pole uh, magnetic field produced in the stator, then we would need to produce four poles in the rotor magnetic field also. So we can produce that. So even salient pole, you have seen that earlier, whatever I have shown, that is a two pole salient pole rotor. This is a four pole salient pole rotor. Whatever the cylindrical pole rotor I show here, that is a two pole cylindrical pole rotor. And similarly it is possible to have four pole cylindrical pole rotors also. So cylindrical pole, what can you see? It is whether it is under the pole or in the interpolar region, everywhere the air gap is almost the same, or actually is the same. So that is why, because the rotor is cylindrical, so it is known as cylindrical pole rotor and cylindrical pole synchronous machine. Similarly, if the poles are salient poles, that is under the pole and in the interpolar region, the air gaps are quite different. So that is a salient pole rotor. And if we have this type of rotor in a machine, that is known as salient pole synchronous machine. Now as we have understood synchronous machine, I would quickly indicate what do we mean by permanent magnet synchronous machine. That is exactly same. If one knows synchronous machine, then permanent magnet synchronous machine is also by default known. There is no need to separately understand that. So would erase these portions. So also as we understand that, we will understand what is the benefit, what are the benefits that we can get out of a PMSM compared to uh, a synchronous machine, a wound rotor synchronous machine. So here, so what we need to get? We need to get a stationary magnetic field in the state in the from the rotor. So we can produce that either by putting some coil and passing some constant DC current through it, or we can simply put a permanent magnet. You can simply put a permanent magnet like this, whose this upper side is north pole and the bottom side is south pole, and similarly another permanent magnet here, whose this surface air gap side is south pole and inner side is north pole. So what do we gain out of that? You can see that there is no need to pass any current through that. So there is no need of any slip rings that is required to take current into a rotating body. So we are eliminating slip rings if we have permanent magnets on the rotor, and if we rotate it, if that rotates at the synchronous speed, then we create a rotating magnetic field that is stationary with respect to the stator magnetic field. Now what else do we see? Do we save? You can see that permanent magnet inherently has magnetism, so it has magnetic energy, so it is a source of magnetic field. But if we have to have wound field induction machine, or the wound rotor induction machine, that is if we have to put, if we need to put some winding into the rotor, then we need some space to put those windings, right? So we need so for creating the same field, because we can accommodate the magnet in the yoke region itself, or in the rotor itself, within that space, it takes lesser space. But if we have to put windings into the rotor, and that will produce a magnetic field, and we have to put iron to provide path for that magnetic field, so you see that you need a bigger volume, or uh, bigger area, or bigger volume basically, to create the same strength of magnetic field. So inherently, because the second magnetic field strength we are getting from permanent magnets, and we do not need to put any uh, winding on the rotor, so inherently you see that we save some space, as soon as we go for permanent magnet synchronous machine. Along with that, there is no slip rings to take the current into the rotor. And you see that slip ring is the most is thing that is continuously in friction, so there will be some wear and tear with years. So these will require continued or recurring maintenance. But if you replace the slip rings itself, then the motor becomes quite robust. So we have, once we go for PMSM compared to a wound rotor synchronous machine, then you see that we do not need to put winding on the rotor. That means we do not need slip rings, and additionally we can produce the same strength of magnetic field by using some permanent magnets which are smaller in size. So we save in terms of volume also. So for the same power rating, the motor becomes smaller. So these are inherent advantages of permanent magnet synchronous machines. Okay, so also just for sake of completeness, for these PMSMs, the magnets, so if this is rotor, the magnet can be on the surface. So this is the rotor, this is the regular rotor, and the magnets can be on the surface. So that is known as surface mount, so SPMSM basically. surface mount PMSM, and or we can this, if this is rotor, we can have the same magnet inside the rotor also. So same thing, it will be north south, uh, north south, it is same. So this is called interior PMSM. And there are many ways to put the winding, put the magnets, all those things. I'm not going to discuss as of now. It is doing the same thing, it is just producing magnetic fields. Now there are structures, how can what are the questions? So how what in what all directions can you put the magnetic field? So instead of a simple magnet like this, it is possible to put two magnets in V shape like this. Similarly, this side is north, north, south, south. So same thing, it is possible to put in V shape. Probably I have just put it in the wrong way. Yes, so it is possible to put things like this. So this is south, this is south, this is north, this is north. So there are n number of ways how you can place these magnets, and also you can place some winding, some magnet, all those things can be done. So the basics remain the same, you need to have some stationary magnetic field from the rotor, and this is how you generate it. So this is about the first kind of electrical machine, that is the simplest, I would say. So that is the synchronous machine. So I will just briefly stop. If anyone has any question, they can ask. Any question?
Yeah, Samrat, I have one question.
Hmm.
Can you go to 35 slide number?
Yes.
Sorry, 36, I think. There you have mentioned like stator field and rotor field, right?
This one?
Yeah, this one. Yeah, yeah.
Okay.
So here you have told the one which is going ahead will be
Yeah.
transferring the energy from there to
That too?
the
Yeah.
one which is lagging.
Lagging. Yes.
So how would you decide that it is going ahead or behind?
In
Because
terms of the
both are running
rotor
at
speed.
synchronous speed, right?
Yeah, yeah. In terms which way the rotor is moving. So if the rotor is moving in this anti-clockwise direction, this is
Okay.
separate, right? Both are
Yeah.
rotating, and rotor is rotating also. So if rotor is rotating at the in the anti-clockwise direction, then this is the leading one and this is the lagging one. If
Yeah, yeah.
rotor is moving in the anti-clockwise direction or clockwise direction, then Fr is the leading one and Fs is the lagging one. So it depends on the rotor speed.
Mm, it depends means
Just
both are at
no, no.
synchronous, right?
Actually,
Yeah, come again. Yeah.
If you said like it depends on the rotor speed. So
Rotor, sorry,
both
sorry,
are at
sorry.
sync.
Rotor direction of rotation. Sorry, rotor direction of rotation.
Samratji, actually,
Okay, okay.
Samratji, just
Yes.
the difference, confusion point is like you just separate it as a field of the stator and the field of the rotor, and then the
Yes.
rotor is the only moving part like that. You just give a differentiation so that he'll understand.
Okay. Uh, so probably I can draw it like this. So this is the rotor. This is the rotor which is rotating. Okay. So this is rotating. This itself is the rotor speed. Now there is some field produced by the stator. This is stator field which is rotating, and there is a field produced by the rotor also, if rotor. Now the rotor itself is rotating. Now with if rotor itself is rotating, something is ahead and something is behind with respect to that, with respect to the direction of rotor motion. So you can see that because the rotor is moving anti-clockwise, so the stator magnetic field is ahead and rotor magnetic field is behind. So that means stator magnetic field is leading the rotor magnetic field. To give an instance here, so at this point of time, in this picture, rotor magnetic field is here, right? And if I run the animation, you can see that the rotor itself is actually rotating in the counterclockwise direction. So the rotor itself is moving in the counterclockwise direction. And if I excite the stator, and at that same instant the stator magnetic field is somewhere here, that means the stator magnetic field is leading the rotor magnetic field for that initial position. But if the stator excitation is such that the stator magnetic field is not here but it is here, then the stator magnetic field is lagging the rotor magnetic field. Is it clear?
Just a minute. Now,
Yeah, this one is
actually,
clear.
Yeah,
But
this
my
yeah,
continue.
you
question,
ask Nagaraji. Yeah, you please ask us.
yeah, the one which you have explained now is clear.
Yeah.
But uh, is my understanding correct or not? You just tell.
Uh,
Suppose if it is a motor, first
uh,
we will give the supply to the stator.
uh.
So the stator will run at first, the stator
So
magnetic field.
stator magnetic field is running. Yes.
So it is leading the rotor magnetic field by some
Yes.
angle. So it
Yes.
is transferring energy from stator to rotor.
Yeah.
So if we consider a generator,
Uh,
we will rotate the rotor first.
yes.
So it will the rotor magnetic field will lead the stator magnetic field.
Yes.
So the transfer will be opposite, right?
Yeah. In terms of so it is very clear if we start from so what you said is correct. If we are running as motor, then we'll excite the stator first. Then the rotor will so stator magnetic field will start rotating, and rotor will try to catch up with that. So that means stator magnetic field is always leading the rotor magnetic field. And if we are doing the opposite way, then yeah, it is generating action. But if we suppose if it is rotating as a motor, if we want to transfer, if we want to change it to generation, then we can just change the excitation in such a way that if we know that where is the rotor magnetic field, if we change the or make the
Sequence.
stator magnetic field lag, we just change the excitation in such a way that it lags, then
Yeah.
instantly it can shift from motoring to generation and generation to motoring like that.
Okay, now I got it. Yeah.
Okay. Someone else is also asking something.
Yeah, the thing is like creation of the magnetic field is more important here. The thing is like if I'm creating whether it is on rotor side or stator side, that clearly it tells like whether it is a motoring action or a generating action, right?
uh, but in motoring as well as generating, we have to excite both, right?
Yeah,
In
so that's
generating
what like
also we need to, yes.
in synchronous machine like we have to excite doubly like doubly excited machine we'll call it. If it is a permanent magnet, if it is there means no need of excitation. If it is
Excitation, that means rotor
there
is already
uh,
excited.
rotor is already excited. If it is not the like no like if it is any electric pole, like if I have an electric from the electric pole, if I wanted to create mean 100% we have to give a DC excitation, correct?
Correct, yes, that is
Yeah.
correct.
So, this is in the case of synchronous machine. So
Yes.
here, just a minute, go back to the previous slide only.
Okay.
Yeah. Now, one is field of the rotor, and then one is field of the stator. So if
Yes.
my rotor, if it is rotating physically, and that speed and my rotor field also is there. That field speed both are same, right?
Both are same. Yes.
Uh, and
Because
the
it
thing
is
is, the
DC.
difference is if it is DC. Like in any case, we excite normally rotor by AC. Is it any case we will not do, right? That is not the
We will
like
do. We will
always
do
we have
in.
to excite.
No, no, we will do. In induction machine, we have to excite with
Uh,
AC.
in
That is what will
induction
come
machine will
later.
do, but in
Next year.
yes, yes, in synchronous machine will not do, right? That one.
Will not do. Will not do.
Yeah. Okay, right.
Yeah. Okay. So probably I'll briefly start for the next case. If there is no more question. Okay. So next what we'll discuss is again we forget what was there in the stator. This is a no excitation in the stator, and we know how to produce a rotating magnetic, or if we have some winding in the in if we have some slots in the rotor, then we know that how to make a distributed winding such that such that we can have a rotating magnetic field. So here I have indicated the color basically shows which phase conductors it is. So from all these cases it is basically cross all these conductors. I have already discussed that if we have a number of slots, so say here the number of slots that I have taken is 30. So I want two pole production. Now for that the critical number is slots per pole per phase. So what is the number here? 30 divided by, we have 3 phase, we have 2 pole, so 5 is the number. That is why we have a phase belt of 5 slots, which together make one red cross band and again a red dot band. So if it is like this, then you can see that the red phase axis will be somewhere like this. So similarly, if we similarly for yellow phase and blue phase once also. So yellow phase and blue phase, if it is if the winding pattern is like this, then because this is all these are cross and all these are dot, so this is the phase belt. So you have y phase axis like this, and similarly for blue phase axis, this is the blue phase axis, right? So we can with the same knowledge of distributed winding, we can make that winding on the rotor also. And now if we excite using slip rings only, but as of now in the first case we'll keep the rotor stationary. That is, the rotor, just for the sake of understanding what is happening, the rotor is stationary. So the rotor is still stationary, and say we excite the 3 phases with some balanced current of 10 hertz. Just for the sake of an example, let us say we take some 10 hertz current. So if 10 hertz is the current, what is the time period? So it has to be 20 millisecond by uh, so into 5. Is it correct? So it is 100 millisecond, right? So 100 millisecond will become the period for that. So if we excite it, let us see what happens. We can see that there is some rotating magnetic field, and it is rotating very slowly. Just to see where it started from, the initial magnetic field direction is here, right? It started from here. Now as I run this thing, as I run this thing, you can also look at the time. Okay, this is the animation, so I should draw here. Right, this is the initial magnetic field axis, and once it runs, yes, so once it runs, you can see that it is quite slow. It has almost completed 20 milliseconds. It is ahead of that, but it is yet to complete its one rotation. Now it is continuing. Now you can see that we have we have we have moved ahead in time by 50 millisecond, and it has rotated by 180 degree. So it is correct that it is rotating at 10 hertz. So because we are exciting the rotor with 10 hertz excitation, and the rotor is stationary, so the rotor magnetic field is rotating at speed corresponding to 10 hertz, which is nothing but 60 into 10, that is 600 rpm. So the magnetic field, rotor magnetic field, is actually rotating at 600 rpm, that is corresponding to 10 hertz. Now what happens if we run the rotor? Say if we run the rotor at 2400 rpm, while the windings are excited with AC currents, what will happen? Let us try to see. So the initial magnetic field, here there are two things that you need to notice. Initial magnetic field is here, and it is actually at the middle of the R phase conductors. R phase conductors, there are 5 conductors, so it is exactly, it is passing through the middle conductor of those middle slot of those 5 slots which are occupied by the R phase conductors. Now I'll rotate, I'll start the animation. You can see that the magnetic field is rotating, and yeah, after 20 millisecond, it has completed in space. You can see that it has completed one rotation, and it has come back to its original position. But what has happened is, earlier the magnetic field axis was uh, along the middle slot, basically here, somewhere here, basically at the along the R phase axis, R phase conductor, the midpoint. But because the magnetic field has some relative motion with respect to the conductors, with respect to the rotor itself, so it is basically moving ahead. It is moving ahead with respect to the rotor conductors. So you can see that in the earlier case of synchronous machine, because the first you probably look at that, it is continuously rotating, right? For 60 millisecond it has rotated, and the magnetic field with respect to a stationary observer like us, that is actually rotating at 3000 rpm. That is same as the stator, or the stator magnetic field, whatever speed it is rotating. Now in this case, rotor magnetic field is also rotating at 3000 rpm, but it is realized by two things. One is the rotor, that itself is rotating at 24,000 rpm in the anti-clockwise direction, and additionally, because of the excitation, the rotor magnetic field omega fr, that is rotating at 600 rpm with respect to rotor. Now the rotor itself is rotating at 2400 rpm. So the speed of the rotor magnetic field with respect to stator, by the principle of relative motion, it becomes 2400 plus 600, that is 3000 rpm, and that is the same thing that you can visualize here also. If I go back and run it once more, you can see that slowly, because the magnetic field is moving ahead of the rotor conductors. Earlier it was along the R phase coils. Now it is moving ahead. In between it came in along the blue phase. Now it has okay, I'll move time instant by instant. Yes, now you can see that the magnetic field is along the R phase middle R phase conductor. Now after some time duration, you can see that it is moving ahead, and now it has gone into the blue phase belt. Now also it is in the blue phase belt. It has gone into at the middle of the blue phase belt, right? Now if I continue rotating, the field will move ahead of the blue phase belt also and go into the yellow phase belt. Now as I move ahead, the yellow phase belt, it has moved at the middle of the yellow phase belt, and if I continue, it will again go and enter the R phase belt, but the opposite side R phase belt. Now it has moved at the middle, so exactly at 50 millisecond it has come halfway. So earlier the magnetic field was in the other side R phase belt. Now after 50 millisecond it has gone to the opposite side R phase belt. So this is the animation that shows you that in this case the rotor magnetic field that itself is rotating because of AC current excitation, that is rotating with respect to rotor itself. And if the rotor also rotates, then utilizing the relative velocity, the relative speed of the rotor magnetic field can be equal to the stator magnetic field. Now you can see that the basic thing, the thing is NR. So basically omega Fr, that is the rotor magnetic field speed with respect to rotor plus rotor speed, that has to be equal to the synchronous speed. Now it can be anything. It can be either so in terms of, if I write in terms of frequency, FFR plus FR equal to Fs, it is 50 hertz, so it can be 40 hertz, or basically 10 hertz, 40 hertz, 45 5 hertz, 45 hertz, 48 hertz, 2 hertz. You can have all those combinations by which satisfies this thing, so that the relative speed of the rotor magnetic field becomes equal to the stator magnetic field. That is the constraint, only constraint. Now probably we'll stop here for any question. Next we'll continue next day. Is there any question?
So the condition for torque production should be the field should be 90 degrees between each other, right?
No, field need not be 90-degree. Field can be at any angle in between 0 and 90 degree.
Okay. For maximum torque, it should be 90.
Yes.
Is that right? Okay.
Yes. So that is about maximum torque. So basically the stator magnetic field and rotor magnetic field, the difference should be 90 degree for maximum torque. Maximum torque.
Okay.
And actually in induction machines, that is the natural case, 90 degree. Just like in DC machine, or we are yet to discuss DC machine because that is the most complicated one. But DC machine also we can have 90 degree phase shift between stator and rotor naturally. Induction machine also we can have natural phase shift of 90 degree. But in unlike these cases, synchronous machine we cannot have. Synchronous machine you in no load condition it will be 0 degree. If as you go on increasing the load, this angle delta will start increasing. But if you go beyond some angle, say 20 degree or beyond that 20, 25, 30, I forgot what is the exact angle, maximum torque angle. In power system also it is discussed. So that is the maximum angle at which the two things can go. Otherwise the synchronism will get lost and synchronous machine will not operate. So yeah.
So here difference between now that omega r and omega as you wrote that equation, right? Like omega fr, can I call that as a slip speed?
Yes, omega fr is the slip speed. Omega
Okay.
fr is the frequency. If the rotors have some current, right? So this is the
Yeah.
rotor current frequency, which is same as the slip frequency, because this
Okay.
is omega s minus omega r. So slip frequency is nothing but the rotor current frequency. We'll see that. So as of now, I am giving some excitation in the rotor. Next we'll ask, do we actually need to give that excitation, or we can get the same phenomena happening naturally, or without giving any physical excitation from outside. Next we'll
But
ask that
generally,
question.
in induction machine, either you excite stator side or rotor side. No need to excite both in the induction machine, correct?
Both side also you can excite. There is something called doubly fed induction machine, which are widely
Okay.
used in wind turbines. So
Okay.
they are excited from both
But
sides.
this difference, the rotor speed and then synchronous speed, the difference needs to be maintained. Though if it is we are
Yes,
exciting, that
yes,
difference supposed to be there. If the
yes.
difference if it's not there, means like again like there will be a, no torque production and that same
Yes,
concept will come.
yes, that is true. So in induction machine, we have to maintain the difference. So
Yes, yes.
say if we are exciting stators with omega s frequency, and we are exciting rotors at omega fr or omega fr frequency, then the rotor speed will be decided by this thing.
Yes.
Rotor speed has to be, so this omega s has to be omega fr plus omega r. So this omega r has to be omega s minus omega fr. This has to hold good. Actually, what is the benefit of doubly fed induction machine? You can, so for generation, normal, if you do not give any excitation, I'm just mentioning that you need to go ahead, or basically above synchronous speed for generation. But in case of basically the rotor speed has to go above the synchronous speed in order for generation. But if you have doubly fed induction machine, you can generate either super synchronous or subsynchronous, and at any speed you can generate. That is the freedom you get if you excite from the two sides. That we'll see, but we'll first understand the basics here.
Yeah, just once again, can you go back to the 37th slide once? 37 or 31st, where we were discussing about that field of stator and field of rotor here. So
Yeah.
in this, uh, now my stator field is rotating with the Fs, and then my rotor field is rotating with something called Fr. Okay.
Yes, yes,
Yeah, WFR or whatever you call it.
yes,
Now, the moment where my stator field and rotor field, both if it gets equal,
Yes.
So if it gets equal, then that case no torque production. Some point you have mentioned, right? In this
No, no,
point,
no.
particular point.
No, no. I said if they for continuous torque, the Fs and Fr, their speeds
Hmm?
have to be equal.
Okay.
If Fs and Fr get aligned like this, so that
Okay.
there is no angle between them, then there
Uh-huh.
will be no torque production. For torque
Yes, that's
production,
what.
there has to be some angle between, say Fs and Fr. There has to be some angle between, delta angle between.
Yes. Yes. So in
Yes.
this case, no, normally if delta is, see, normally if delta is zero, so
Yes.
like both the fields are running at same speed.
No,
So
no,
then there is no torque production, correct?
no, no. Fs and Fr both are running always in same speed. When delta is 0, then they are together. They are like collinear vectors. They are both
Okay.
are running together. So there is no angular
Okay.
displacement between them. If it is the circle, at any instant, if Fs is here,
Okay.
Fr is also here. At another instant, Fs is here,
Okay.
Fr is also there. So that means both are running at the same speed. So there is no torque
Okay.
production in
But
this
delta is
case.
okay.
If
Okay. But
delta is
always
non-zero, yes.
okay. Okay.
So
So either FS and FR both, if it is, I'm assuming if it is running at 1500 RPM, but there's
yes,
supposed to be a like small angle, then only torque production will happen. If it
yes,
is not, there is a delta. If it is, it will become zero, means there is no torque. Correct.
yes, yes, that is correct.
Yeah. Yeah. Understood.
Okay. So next class will start understanding what happens. So understand, basically the basic question that you will ask is whether we understood how to produce a rotating magnetic field by exciting some AC currents into the rotor such that the relative speed of the rotor magnetic field with respect to the stationary observer or stator, that becomes equal to the stator magnetic field. That we have seen that we there are two things we are utilizing this relative speed concept. So the rotor itself is rotating at omega r, and the rotor field with respect to rotor is rotating at omega fr. So with respect to a stationary observer, this rotor field is actually rotating at omega fr plus omega r, and if it is maintained at omega s, then we can have the criteria for torque production fulfilled. That is, two fields that are rotating at same speed with some angular displacement. Next day, the question that we'll ask is it actually necessary for us to give the second excitation into the rotor, or we can have some case where naturally it will take care of it itself. So that is where we'll start the next day session. Okay, so shall we close now?
Okay.